In this experiment, we are going to study weirs. A weir is a small dam, an obstruction in open channel flow. The difference is that a dam is built for creating a reservoir, and a weir is built for elevating the water level. The elevation of water level can allow larger cargo ships to pass through and can increase the flow velocity when the water drops down from the weir, increasing the efficiency of the water-generated power. Weirs were often used to power up saws, mills, and factories hundreds of years ago when the electricity was not yet invented. Back then, the moving water was the most consistent source of power available in large quantity. Let's find out how weirs work. When a flow encounters a weir, the water level has to rise up to pass over the top of the weir, which is called crest. By increasing the water level, the weir slows down the velocity, creating a subcritical flow in the upstream. While the flow is passing over the weir, it begins to draw down with the depth decrease and the velocity increase by the gravity and the water contraction, making the upstream flow supercritical. This region of flow over the weir is called nap. As you can see here, the taller the weir, the higher the water level rise in the upstream, which results in faster downstream flow with more kinetic energy. There are many types of weir. Examples are sharp crest weir, which is a plate-like weir over the cross-section of the channel, ogee weir with a curved edge, and a bolt crest weir, which has an extended crest length. Why are there many different types of weir? Because a weir's job is not only to make the downstream flow move faster, increasing the kinetic energy, but also to regulate the water level in the upstream. When there is a drastic increase of discharge or flow rate, like a thunderstorm, a good weir can control the upstream water level to allow only slight increase of the water level. This is useful in flood control. The relationship between the weir head H, which is the water level above the weir crest, and the discharge rate or flow rate is described in weir discharge rating curve. An example of such curve is shown on the right. The equation of discharge rating curve can be expressed as Q equals square root of 2G multiply CL and H to the power of 3 over 2, where H is the weir head, L is the width of the weir, and C is a coefficient depends on the geometry of the weir. The larger the C value, the flatter the rating curve. That is what we want. That means, despite of large change of the discharge on the x-axis, the y-axis, weir head, only change a little. It turns out the most efficient geometry is the one that matches the shape of the lower nap of a sharp crest weir, which is called ogee shape. That's why ogee shape weir is often preferable. In addition, underneath the nap of a sharp crest weir, there is a region of entrapped air which supports the curvature of the nap. Over time, the water flow takes away the air and decreases the air pressure, making it shrunk. Once the entrapped air gets completely taken away, the nap may clap. That could cause a decrease of the efficiency of the water transportation, resulting in a decrease of the weir coefficient. To avoid that, an ogee shape weir is again preferable. You will observe this phenomenon when you study the sharp crest weir in this experiment. One important thing need to be noticed is that The weir coefficient has been found as a function of h over p, as shown in this graph, where h is the weir head and p is the weir height. In this experiment, you will have weirs with different height. How can we compare the coefficient if the weirs' heights are different? As you can see in this graph, if the p over h greater than 1, that is, your weir head is less than your weir height, the coefficient actually does not change much. That means if you can keep the weir head less than the weir height, which is likely the case in this experiment, the coefficient is almost independent from the weir height. So the coefficient of this weir could be comparable. A broad-crested weir is often used as a measuring device to get the value of discharge Q. In practice, discharge Q is a factor that is not trivial to measure. This provides a way to measure it. If the weir's nap is not completely submerged, the extended length of a broad-crest weir provides a transition of the flow from a subcritical state to critical state. The flow stream above the weir is actually in critical state, with the flow number equal to 1. The depth of the water measured above the broad-crest weir gives the critical depth, Yc. According to the flow number equation, the relationship between critical velocity Vc and the critical depth Yc can be set as Vc over square root of Gyc, which equals to 1. And we can get Vc equals to square root of Gyc. If we know the width of the weir b, which is a constant, we can calculate the discharge as Q equal to Va, which equal to VcBYc. A weir can increase the kinetic energy of the flow, making the downstream supercritical. However, we want to tame the flow velocity once it passes a certain point, and this is usually done with the hydraulic jump. We have learned property of hydraulic jump in previous experiment. It occurs when supercritical flow encounters a subcritical flow. The location of the jump is also dependent on the flow number before the hydraulic jump, which can give a prediction of a downstream water level. In case A, if the predicted downstream level Y2 is less than actual value Yt, the hydraulic jump will occur some distance away from the weir. In case B, where Y2 equal exactly to Yt, hydraulic jump will occur right next to the weir. We have seen both cases in previous hydraulic jump experiment. Now, in case C, where Yt is greater than Y2, the hydraulic jump gets submerged by the downstream flow. The submerged hydraulic jump creates an area of recirculation that can trap and drown the swimmer and kayaker, and they will only be able to escape if they can manage to pass the boil point. This condition is also called drowning machine, a dangerous zone created by low head dam. This trapping zone will get dissipated when the Yt gets much larger than Y2, as shown in case D, where the nap gets completely submerged. You'll see all these phenomena in this experiment. In this experiment, our goal is to develop the weir discharge rating curve for 3 different weirs and compare the weir coefficient. In the experiment, we have 2 weirs sitting in the flume. The broad crest weir is near the inlet. The sharp crest weir is at the center, which will be later switched to the ogee-shaped weir. After you set a flow rate, turn on the flume and wait for the water to come in. You can see the broad crest weir, which is near the inlet, blocks the flow and makes the water level rise in the upstream. Once the water level gets above the water height, it overflows and passes the weir. Since we have another weir in the downstream of the broad crest weir, a hydraulic jump formed and moved towards the weir. Once the flow in the entire flume becomes stable, we can start taking measurements. As we mentioned earlier, a broad crest weir can be used as a measuring device for the discharge value. To do so, you need to take the measurement on the depth of the water above the weir, which gives you the value of the critical depth. Next, to get a data for the weir discharge rating curve, you need to measure the water head in the upstream. Passing the weir, the flow creates a hydraulic jump submerged by the downstream flow that causes an area of recirculation. The recirculating currents can trap anything from escaping. If you throw in a ping pong ball, you can see it cannot go with the flow to the downstream, but get trapped. Next, we are going to look at the sharp crest weir and take the measurement of the weir head. There is a ridge of air underneath the nap of the sharp crest weir. The flow will gradually take away the air. This entrapped air can sustain because there is a channel for ventilation. If we close the channel, the entrapped air will diminish and eventually disappear. Once you finish all your measurement using these two weirs and try it at different flow rate, TA will help you to switch the sharp crest weir to an auger weir. You just need to repeat the measurement using the auger weir. In order to get enough data to complete the discharge rating curve of weirs, you need to repeat the same measurement for different discharge value from 10 to 100 cubic meter per hour at a step of 10 and finish the datasheet. Here is an example of how to analyze the data. Given the discharge Q equals to 60 cubic meter per hour and the width of the flume B equals to 30.9 centimeter. From a broad crest weir, we measure the critical depth YC as 5.3 centimeter and the weir head H equal to 10.5 centimeter. Ask, what is the discharge value according to the critical depth YC? What is the percentage error in comparison with the set value Q? And what is the weir coefficient of the broad crest weir? First, we can use the equation of flow number for critical flow, of which flow number equals to 1. By substituting the critical depth YC equal to 5.3 centimeter, we can get the value of the critical velocity as 0.72 meter per second. Next, the calculated Q value equal to V multiplied by area A, which equal to VCB YC. Substituting the previously calculated value, we get the calculated discharge as 42.44 cubic meter per hour. And the percentage of error in comparing with the set value 60 is about 29.27%. This percentage error is quite large, which may come from multiple sources. First, we haven't calibrated the flume, and we don't know how accurate the set value Q. Second, there may be some assumptions in the equation which are not satisfied in the experimental condition. Next, using the weir discharge rating equation, we can get the weir coefficient as C equal to Q divided by all other terms on the right side of the equation. After substituting the value of the known parameter, we can get the weir coefficient as 0.37.